So let's learn how to analyze some data. What I have here are the insurance charges for 1,338 health insurance customers. So this is their charges for the year. Then we also have the region of the country they live on, whether or not they smoke, number of children, body mass index, which is a function of your weight and height. Higher numbers mean you're heavier for your height, sex, and age. So we're hoping to learn how to use these variables to predict how much they're going to charge. This is a very common task in organizations. So before I get to predict charges, I'm going to start by looking at the individual relationship of charges with each one of these other variables. So let's start with the numeric variables. What I want to do is characterize or understand the relationship between just age and charges to begin. Actually, let's go. I'm going to do BMI instead. Here's why. What I want you to do is download this data set, open it up, and go ahead and select the entire column. So click on column C, column G, and then we're going to go to Insert, and then this little diagram, or this image right here, it's a scatter plot. So click on this very first one, and we get this chart right here. So I'm going to call this charges by BMI. So each dot, you're probably hopefully familiar with this from high school algebra or middle school algebra, and each dot represents one of the rows. So this one right here is, if we hover over it, it might give us, there we go, charges point 4741, so that's a BMI of 4741, and insurance costs of 63,770. All right, down here we've got someone on the opposite end. Small BMI, 15.94. And charges of 1,694. So this scatter plot tells me the relationship between charges and BMI, and as I look at it, I feel like I can see a couple of different groups here. In general, if I take it all in, it looks like it's going up, meaning as BMI gets higher, charges gets higher as well. But we don't know that for sure. I mean, it's tough to tell because see how many of these dots are overlapping each other, making it difficult to see, well, just how many dots are down here, how many over here. It could be that the line doesn't go up because we don't know about the density of these dots. So there are a couple of statistics we can calculate to help us understand the visualization a bit better. Let's start with a Pearson, let me relabel this, Pearson Correlation coefficient. And you probably remember this from, well, hopefully somewhere in high school. There we go, coefficient, close enough. So R is how we denote that. You can calculate this in Excel. Look how it gave me the R symbol. You know what, good enough. We're gonna stick with it just because that's kind of cool. All right, so Excel has a calculation for this. You may have learned this before in another class. If so, fantastic. Correlation, all it wants is the list of the two arrays. An array is a list of numbers, so I'm gonna grab all the charges. And it doesn't matter which array I put first, not a problem. And then it wants the second array, which is going to be BMI. Now I'm not including the header. I hold Control-Shift down to go and select everything all at once. Close my parenthesis in the formula bar, enter. All right, so my Pearson correlation coefficient is 0.198. So if you remember, these things vary between -1 to 1. 0 means these dots would be more scattered and spread out, whereas 1 would mean they're on a perfect straight line going up, and -1 would mean they're in a perfect straight line going down. So this helps us understand how close together along a line these dots are grouped. Now, because it's closer to 0, it's not in the shape of a line very well, and you can tell that. That doesn't mean that it's useless or that BMI is a bad explainer of charges. In fact, this could be what we call a statistically significant relationship, meaning that if we were to collect another 1,000 customers, we would expect the relationship between BMI and charges to look just like it does here. So this is a useful measure, and it does tell us whether the relationship is positive or negative. So we can confirm now that as BMI goes up, insurance charges do indeed go up. So the slope of this is positive. However, we don't know what the actual slope is, and we don't know if that's significant. So here's what we're going to do next. I want you to click on the image here, and then over here on the plus sign, go to trend line, and here's our line. It's tough to see. I want to do some formatting to make this easier to understand. So I'm going to go to my format here. Actually, maybe what I'll do is I'll right click and go format chart area. There we go. That brings this box up over here for us. I can click on my trend line and I can format it to be solid, gradient, automatic. I can decide what it looks like at either end. Notice that it comes right down here. I think I want to make my color something else so it stands out a bit better. Let's make it black. There we go. So now we can see it over the top of the dots. And I want to add some other features to it. Let's go here to, there we go, this one right here. And I want to display equation on the chart and display R squared on chart. I'm going to move this up here so it's easier to see and out of the way a bit. All right, this is our good old friend y equals mx plus b formula. Hopefully you remember this too. This says right here that the slope of that line is 39387. That's a really tall slope. Well, it actually makes sense here because our scale of the charges is so much higher than our scale here on BMI. So even though that looks like a fairly flat line, it's actually really steep. So that means that a single unit increase in BMI is going to increase your predicted insurance charges by almost $400. And if your BMI were 0, which is impossible, then your charges would still be 1,192. That's where this line crosses the y-axis right about there. I bet there's a way we can actually make this extend even further, but I'm not going to worry about it right now. So this equation is useful. We also get this value down here of r squared, 0.0393. What is that exactly? Well, I'm going to say this equals that times itself again. There we go. There's that number. R squared is literally just the square of r when we're using only a bivariate, when we're comparing just two variables together. R squared, the statistical explanation for that is it's the percent in charges that is being explained by BMI. Well, that doesn't seem like a whole lot. The percent of charges explained by BMI. But here's a nice way to understand it. I'm going to insert some shapes here. There they are. And I want a nice circle. Close enough. Draw this right here. I'm going to copy it. All right. I'm going to fill this one in. Orange, oops, not, well, that'll work. And then fill is up here. Fill it with orange, beautiful. Okay, so I'm going to write on this one. I'm going to say this is charges, and this one is BMI. So what that r squared is telling us is that these two circles overlap by only 4%, something like that right there. So this circle represents all of the variation in charges from 60-something thousand down to 0 or 1,000 something, whatever that is. And then BMI, this circle represents all the variation from about 15 up to 53 or so. And so the more this circle crosses over charges, the more it explains charges. So the more accurate this line is at predicting what your charges will be based on your BMI. And since r squared is 4%, that says that these circles overlap only about that much or so. Does that mean that BMI is useless? Not in the slightest. Companies are willing to pay a lot of money for a 4% improvement in prediction. As an example, Netflix in 2009 created a competition, a famous one, where they offered $1 million to anyone who could improve their prediction by only 7%. Their goal, they were hoping to get 10%, and that got beaten. That's a great story, but anyway. But Netflix was willing to start paying out on that $1 million to anyone who could make a 1% improvement or better. They would give these bonus prizes for anyone who could make some incremental progress. So a 1% improvement is nothing to laugh at. So we've got a pretty good characterization now of the relationship between BMI and charges across all of these things. We can also calculate a p-value based on this, but I'm not going to worry about that for right now. Excel doesn't do it automatically, but there are other ways we can get that. But the p-value, if you may remember, any p-value less than 0.05 is what we call statistically significant, which means that this is the probability that if we were to collect more data, that the next scatter plot on the new data would look different from this. So I noticed from experience the p-value here is going to be below 0.05, even though we're not going to get into it. And so what that means is there's less than 5% chance that when we collect more data, it will look different than this does. In other words, it's going to look the same. We can count on this relationship between charges and BMI. All right, so the next thing we should do after we've calculated this is to recreate this for every other variable. Now you can do that on your own. I'm not going to go and just repeat myself, but I do want to show you one other thing we can do. We can create what's called a correlation matrix. So I'm going to put all of my number variables together because this only works for numeric variables. So I'm moving these categorical variables over here. So categorical variables simply are words that have no ranking to them, whereas numeric obviously have numbers. Now, you can have you can have exceptions to both rules. By the way, for example, you could have a variable called region, where southwest is a 1, southeast is 2, northwest is a 3, northeast is a 4, and you can go through and assign those numbers everywhere. That looks like it's a numeric variable, but it's not, right? Because these are just unique identifiers. There's not actually an order to regions. You can't say that southeast is more of a region than southwest. That just doesn't make sense. With categorical variables, there is no order, and we have other ways to represent these, which you'll learn about in the next chapter. So just because something's numeric doesn't mean it should be counted as a numeric variable and that we create a scatter plot for it. Similarly, it could be that you have something like children and you have this instead. So here I'm just typing out the numbers for the values that are right there. If you have data like this is not very common, but it does happen, then you're going to want to convert this to numbers so that you can then treat it as a numeric variable. Just because it's written out in text doesn't mean that it's a categorical variable. So you have to understand the meaning behind each one of these variables before you divide it into categorical and numeric. Anyway, now that I've got that, what I want to do is go to data and data analysis. Now, if you don't have data analysis, then what you need to do is go to File, Options, Add-ins, Excel Add-ins, go. And you need to check this box right here for the Analysis Toolpack. All right, once you check that box, now every once in a while, depending on your laptop, everybody's got slightly different settings. You may actually have to restart Excel, but probably not. Once you do that though, but you should be able to see this data analysis. So select that. And there's a list of statistical functions in here that are super useful. Grab this correlation one, double click. And then the input range it wants is all of the numeric data, including the labels. So I'm going to go here from D1, Control Shift right, and then down, select all of that data. Check the box for labels in the first row, tell it where I want it to print the output. Click that circle first and then put your cursor in here, or else it'll give you some trouble. I'm going to scroll up here and I'll put it right about there on I-21, hit OK. And it prints me out this nice correlation matrix. So here I did the Pearson Correlation coefficient just using the Correl function and manually selecting those two. Here it went ahead and printed out all of them for me. And then ones on the diagonal mean that it's the correlation of children with children, which is a perfect one. Yeah, we don't care about that. Really, they just put the ones there for our eyes to kind of help identify and look at the intersection between each of these. So I also really don't care about these correlations right here, because when I'm doing this data exploration, I'm really just interested in all of the variables correlations with the one that I want to predict, charges. So I'm going to go through this process of creating a scatter plot, calculating a correlation, which I've now done down here, adding the trend line, adding the y equals mx plus b, for each one of these numeric variables along with charges. And I've already done that for BMI. We have it right here. I would just repeat this process for children and then for age. You can put this together in a nice looking report and you deliver it to management or whoever that would be interested in looking at this. So that's it for analyzing numeric to numeric relationships.